This is a simple operator GUI written to use TFI component interfaces for communicating with smart test and driving the testing process. It's written using the Python scripting language and the Python support that also comes with TFI. It's designed to be easily customizable by GSS engineers to meet the specific needs of any customer's production environment. Tabs and functionality can be easily added, and you can see here that this particular implementation has a tab to show various logging data, a tab to start or stop smart test, and a tab to show summary information during testing. Once testing is started, you can also see the tab that shows the testing parameters here. So I'll load the setup parameters from a file by selecting the Setup Lot button, and you can see that the prober handler configuration is automatically updated based on the global configuration setup, and the parameters show up in this window. I'll start the loading process and testing process by selecting the Start Lot button. Once the testing setup is initialized, we can determine if this is wafer sort or package test and bring up the appropriate results display application, which are also TFI-based components. So once testing starts, you can see the results being updated in the main tab here. And as I cycle through the tabs, you can see the parameter tab contains the testing parameters, and the logging tab updates the bin information and can also show index times and all of the tester events as they come through. And from the Summary tab, we can generate partial lot summaries using the Generate Summary button and get results by site as well as overall results. A summary will be automatically generated at the end of the lot and will be written to a summary file by default. At the end of the lot, the buttons on the main tab will be reset for the next lot.
This is the ES dashboard. This is the front page. It will have the site, the tester serial number, the tester name, the workstation ID or host name, the smart test version that was running the last time a calibration was done, the last time that a board was swapped in or out, and then what hardware is available in this system. This is also the history of change. You can see down here of a card that was moved out and a POGO mapping change as well. This is the EM dashboard. This is the real-time dashboard. Where the ES dashboard is historical information, the EM dashboard is real-time information. And you can see that when a tester is actually testing, you can see what stage, what lot ID, the percentage of yield. You can set up a difference in percentage that will set an alarm between sites in case you have a yield fall off. It'll give you an estimate of units per hour and then the current test and index time average, the test program that's running, the smart test version it's running on, and the load board ID. The smart test version will tell you what smart test versions are available on the testers that you have on your floor. These versions are loaded on these testers. You can also filter some of this out and just ask for particular smart test versions. So you only see the boards, the testers that you're interested in. The calibration screen will show you the current status of all of the calibrations. So for each of your testers, each of the calibration types, when they were last run, when they're due next, and if that due date is past or pending. You can also see some additional detail of calibration on a per tester level. You can enter your own type of external reminder for a calibration that is done outside of SmartTest. Hardware configuration presents a tree that's by site and by tester. So here we have, in fact, 4 sites. And I can go to this tester, and for each of these testers, you'll see the icons will show as many as 3 of the most recent calibrations and changes to the configuration. As this is going to be, this icon represents the controller itself. So this is the tester serial number and host name, how many CPUs, what their speed is, and what the workstation model is. This is much more interesting when you get to the hardware configuration of the test head itself, where you can see what's in a digital card cage. You can see the slot layout. You can see specifics about a given card. You can also see a slot diagram. You can see a card cage diagram. You can get a summary of the information in a nice tabular form. You can go to the raw data that will allow you to export the data to a CSV file for spreadsheet view offline. The board trace capability is when you're looking for a particular board type, and you can put in its part number or serial number, and it will tell you where that card is today if it's on any one of your systems. Here we can expand how many of these we get to look at once. I can go to any given card and I can see where it is now. If this card were not brand new in this tester, then you would see an entire history of what testers this card had been in and what the dates were, so that you could see when it had been in spares or when it had been in repair, for instance. And on any given card, you can also pull up the details of what is going on with that. Tester search will allow you to look for particular test head types. If you're looking for pin scale, if you're looking for what have you. You can again go over here and you can put in, this understands wildcards. So DPS star, and it will pull up the testers that just have those on them. So that is a quick look at the ES dashboard.
This is a demonstration of our TFI fault detector. I'm going to go ahead and run a lot here. And we have a simple package test. And this fault detector window, which is not normally up during operator use, is just for debugging, but it allows us to show during this demo the faults that are generated. Now in this case we see there's some calibration checks that failed, and then we also have a data logging check at the beginning of the lot, which means that the STDF file wasn't opened up. So we'll let this run for a couple minutes and we'll see that that's pretty much it for the faults, because I have all the thresholds on CPU, memory, and disk space set high enough that there aren't any faults. In the rest of the demo, we'll show you some of the other faults that the fault detector can check. So I've restarted the fault detector, and we'll go ahead and restart the test program here. I'll pull up the debug window here so we can see what's going on. I removed the check for the calibration and the FPGA, so we shouldn't get any faults now. So as we're going through this, it's monitoring memory threshold for any process. So any process that goes over 4%, which is a very low threshold, should trigger a fault, and we'll see it here in the window. There we have one. And so this is showing that the bin starter process of HP 93000 has gone over the 4% threshold. Of course, in normal operation, we would never set a threshold that low, but I'm trying to demonstrate that this can capture a memory threshold fault. So for example, if you set that up at 90%, which would probably be a more realistic threshold, you would detect any process that uses over 90% memory. So I went in and I changed the threshold for total CPU usage to 10%, and now we see that the CPU usage is failing at 11.8%. Let's go ahead and run the tests here, and I think we'll see that number climb up a little bit. So here you see it went up to 12.3. Naturally, we would never have the total CPU usage down that low. It would normally be up at like 95%, but this could send you a warning if for some reason a process went out of control and was using greater than 90 or 95% CPU usage. So far we've shown a CPU and a memory check, and there's also disk check, and we've also shown a data logging check. Sometimes it's important that a particular test program be run with a certain version of Smart Test, or that it be run in a certain mode, such as an operator mode rather than engineering. The fault detector has the ability to detect modes and parameters. So I'll show a demonstration of that. We'll go ahead and start this lot here. We'll pull our window up here. And at the very beginning of the lot, it immediately flags the fact that we're running with Smart Test version 7.1.3, not 7.1.2. Now that doesn't seem like it might be that critical, but sometimes there's certain patches or something in a newer version or an older version that you want to run with. We also see here that we're running in engineering mode, not in the operator mode that's required. So for either one of these, this could either stop the operation of the test cell, or it could send an email or some other action. So we've showed a few different faults that the fault detector can check. Here's the list of all faults. We have the memory, CPU, disk usage. We have missing processes. You can check if a certain process is running. We can do calibration check. And a really useful one is excessive time between states. If it takes too long, for example, to kick off a lot to fill in the operator information, you could put a 5-minute time limit on that. And if the test cell sits there without that information being entered, it can generate a fault. We can also check, as we showed, the Smart Test version online or offline check user mode. And the FPGA check is a check of the actual hardware FPGA version. We also have the data logging, and even UI report window warnings can generate faults. We've shown quite a few components that make up TFI. All of these components are built on a TFI framework. The TFI framework provides event reporting, which allows you to synchronize your components with events that come out of Smart Test or even custom events. It also provides uniform access to Smart Test APIs, such as the TPI, CPI, an HVM API. These are all APIs that allow you to control or query smart test. But some of these APIs vary across different versions of smart test. TFI provides a uniform interface to all of those APIs so that you can use them without concern for how they may differ from smart test version to smart test version. TFI also provides a test cell communication scheme using IPC, which allows your components to easily communicate with each other. Here we'll see a session of smart test running here, and I want to show you the events coming across here. So this is the tail of the event log showing the events. You can see in here package completed, test flow exec completed, and you can see all of the binning and the site insertions. If I go ahead and pause this, you'll see right here that we had a test program exec paused, and then we had an event dialog started. So these kinds of things are very valuable if you're trying to write a component such as an operator interface that needs to know when certain things within smart tests have occurred so that you can synchronize with them. TFI Framework provides all of that, provides the events, provides the uniform access to APIs, and it provides test cell communication using IPC. The TFI Framework also allows you access to the components that are included in TFI, and that gives you information such as yield, bin counts, statistics, and it even gives you access to our prober and handler control, which means that you can talk to a prober or a handler from a test method, which is usually not possible with just regular smart test. Here I have a view of the smart test server log file, and it gives you an idea of some of the things that you can get out of the TFI framework. Right here we see get temp path, get file state, and let's see what else we see. Get parameter, so that you can go out and get parameters that have been seen by the EDL stream. Again, there we see another get temp path. So much of the information that's available behind the scenes may not be so easy to get, but with the TFI framework, we make that easy and accessible.